Hello and welcome to this short video of my work, benchmarking the utility of maps of dynamics for human-aware motion planning. Let's start with a short example. Suppose there's a robot at point A, marked by the red star, that has to travel to point B, marked by the green star. A traditional motion planning algorithm would return one of two paths, which is R1 and R2. These paths are equally long and hence equally viable. Suppose now the robot also has some visibility around itself, so it can observe live information with regards to people, but it also has some sort of experience that is denoted by these blue arrows. So these blue arrows tell us in what direction generally motion has been happening in this environment. Now, armed with this new information, the robot might actually choose path R1 because it tends to follow the flow, whereas R2 is now against the flow. So the robot might have to maneuver around oncoming entities such as pedestrians, or it might have to pause and wait a lot more. So this blue information is what we call MODs, or maps of dynamics. So dynamics information, of course, is either available live, such as in the immediate vicinity of the robot. That's available via sensors and tracking, and sometimes also via motion prediction. Our experience information, that is MODs, is available after the robot has recorded data and has some experience of the environment itself. Live info, of course, tells us about the object itself, where it is, and where it might go. And here object might mean any dynamic entity, such as pedestrians or other dynamic vehicles. Experience information, that is MODs, tell us how objects have been moving about in an area. So it tells us the motion patterns in space. One MOD we have used is the Gaussian mixture model map. It's a mixture model of trajectories. Here we see a blue trajectory with 4 points, a green trajectory, and a red one. And these are the 3 trajectories available in this mixture model. And these circles represent the standard deviation of this point in space. Another model we use is the cliff map model. This models velocities instead of trajectories. And here each arrow is the mean and represents the heading direction recorded at this particular location and the magnitude of the velocity vector, otherwise called the speed. But we also have a distribution, which is a circular linear distribution. The listener is, of course, invited to please read the manuscript if you require details. The mixture model, of course, it represents the velocity in polar form, that is, heading and the speed. Another map we use is the STEF map, or probability of directions map. Here we have different probabilities of transitions. So at this particular location, what is the probability of going left versus what is the probability of going left down? So this map records the probabilities of transitioning from one cell to the 8 neighboring cells. Motion planning is the problem of finding a sequence of collision-free poses or motions that take the robot from start to goal pose. Of course, let's have a 4-point trajectory. This might be a part of a motion plan or an entire motion plan. What is usually done is that the costs at these individual trajectory points is summed up to obtain the cost of a trajectory. Traditionally, there were 2 components. So you have the CD, or the path length, Euclidean's distance cost, so essentially the length of the path between 2 trajectory points. CQ is the turning cost, or the quaternion distance, so how much a robot has to turn. And then what we have done is added in another cost, CC, which is the MOD cost, and a weighting parameter for each of these. Typically, one might choose a weighting parameter of 1 for WD and WQ, and vary WC according to details, which can also be found in the paper. And why do we need benchmarking? Why new metrics? So new metrics to gauge the utility of MODs to motion planning is what we present in this paper. Why MODs? Because existing work focuses heavily on live dynamics information, and sometimes they also assume that the entire environment is visible to the robot, which might not work out if you want to introduce a robot in an infrastructure-free environment, that is, an environment that does not have the infrastructure that the robot might assume that it needs. And why new metrics? New metrics because traditional metrics aren't really related to MODs. They tell us how long a path is and how many turns a path might have, just as we saw in the cost function. But we would also like to know what the effect of these MODs are. And hence our benchmarking framework is essentially split into 3 steps. So step 1 is collect some pedestrian data that we split in 2 parts. The first part we build the MODs from. The second part, what we do is cut out data at specific durations for execution-based experiments. So we try to execute motions that were planned from the MOD-aware planners, and then we try to measure quantities based on the execution itself, not simply based on the planning step. So then, of course, we use the aforementioned MOD cost functions and generate the motion plans, and we execute those motion plans. So 3 steps, as in with respect to the data, we collect data, split it in 2, build MODs from the first, and then cut out sections of that pedestrian data, keep it aside. Then we plan motions using the MOD cost functions on these generated MODs, and we generate motion plans. And in the end, we execute those motion plans while replaying pedestrian data. What does it mean to replay pedestrian data? We will also shortly see an example of that. The advantages of this simulation framework is that it's highly reproducible and repeatable, which is quite often very hard when you conduct experiments in the real world. We can replay or emulate pedestrian data, which we will again soon see. And it supports multiple robots as well. So you could have 5 robots amidst pedestrians if one would want to. Although in this work we just use 1. Let us see the results. So what happens when we do this experiments is that even a map as simple as the intensity map, which basically counts the intensity of observations at a given grid cell, for instance, and that has a better waiting time than MOD-aware planner. And waiting time here means when the robot has to wait for the pedestrians to pass, or the pedestrians have to wait for the robot. Planners that use both intensity and direction, such as the cliff map and GMMT map based planners, have the best to mean waiting times, and GMMT map itself has the best overall results. So waiting times and success rate of execution. Let us look at a simulation of the using the coordination framework to see what we mean exactly. So here we have the simulator running, and as you can see, the green circles represent the pedestrians. You also have a P240, and that is the arbitrary generated ID number of the pedestrian. You also have a robot that's represented by this rectangle in gray. And we additionally have a status of each of these agents. So for pedestrians, you would see the words moving. For robot, you see driving. And now this experiment will soon end, and the next one will start as soon as the robot reaches its final position. The gray envelopes, as you can see here, are the sweep of the robot's path along its trajectory. Similarly, sweep of the pedestrian's path along their trajectory. And here you see a pedestrian that is not involved with the robot in any sense. So it's moving, and soon it will reach its endpoint, and it stops. Let's go back and see what the robot is doing here. As you can see now, the robot is waiting, and that is because there's a pedestrian close to it, and the pedestrian is moving quite slow. In the coordination framework, you see these precedence constraints. So that tells us what agent is waiting for what agent. Since the robot is supposed to wait at some point down the line for this pedestrian, you see an arrow pointing towards the pedestrian. So the pedestrian in this particular precedence has higher priority. And similarly, you have one over here as well. This means that the path of pedestrian 236 and the robot intersects, and they might have to make way for one another at some point. In this specific case, it was that the robot had greater precedence, so the pedestrian might have to wait. But then it disappears since the area that is contested has already been passed by one of these agents. So the precedent constraint becomes obsolete. So if there are cyclical pedestrian precedence constraints, that is, if an arrow points from pedestrian 236 to the robot, and then from the robot to pedestrian 236, that means they're waiting for each other. That means a deadlock has happened. That is what we mean by the success rate. So that's the percentage of runs that would complete successfully without a deadlock happening. So when a deadlock happens, of course, you'll need a deadlock resolution, and that is usually done via replanning. But we don't do that because we want to preserve the original plan of the robot. So here we see that the robot again is waiting for this very slow pedestrian. This is what I mentioned before about the repeatability as well. You could see that the pedestrians are moving in exactly the same way that they moved before, because it's essentially the same time band that's been cut out. But the motion plan of the robot varies from run to run because it's generated by a sampling-based motion planner. As you can see, this is the contested area between 165 and the robot here, and that precedence constraint has disappeared. Similarly, you might want to check this precedence constraint out, and that means that somewhere along the intersection of these paths there is an area that is contested. That is the critical section, and here it refers to this area. Once the robot passes that area, this constraint is also removed.